Hey Global Impact students, this is Mr. Ellinger. This lesson is on solving systems algebraically. Our learning target is we want to be able to solve linear systems algebraically. Essential understanding for the lesson: a system of equations can be solved by writing equivalent systems until the value of one variable is clear, then substituting to find the values of the other variable. If the equations of the two systems are equivalent, then a solution of the system that is easier to solve is also a solution of the more difficult system. Some background information for the lesson. Two algebraic techniques for solving linear systems of equations are substitution and elimination. Both strategies obtain an equation in one variable that can be solved using the properties of equality. The resulting value is substituted back into one of the original equations to find the value of the other variable. For substitution, the equation in one variable is obtained by solving for one variable in terms of the second. Then substitute the literal expression for the first variable into the other equation and solve for the second variable. Substitution works well when one equation is already solved for one variable, or when the coefficient of one or more variables is 1 or -1 in one or both of your equations. For elimination, the equation in one variable is obtained by adding or subtracting the two equations, eliminating one of the variables. Elimination works well when the coefficients of one variable are the same or inverses. Okay, so we can solve a system of equations by writing equivalent systems until the value of one variable is clear. Remember, we can obtain equivalent systems or equivalent equations by using our properties of equality. Then we substitute to find the value or values of the other variable or variables. You can use the substitution method to solve a system of equations when it is easy to isolate one of the variables. After isolating the variable, substitute for that variable in the other equation, then solve for the other variable. So here's an example. What is the solution of the system of equations? And so again, a system is two equations that we work with together simultaneously. So we have our curly brace here indicating that this is a system. So when we examine our system, we notice right here this y, no coefficient, or a coefficient of 1, implied 1 there. So this is set up fairly well for a substitution problem. So the first step is to solve one equation for one of the variables, and the way that we know which one is to choose the equation that has either just y or just x. So solving for y, I get -2x plus 10. Subtract 2x to the other side. The second step is to substitute the expression for y in the other equation and solve for x. So here you can see is our other equation, 3x plus 4y equals 12. We take out the y and we put in the quantity -2x plus 10 because they're equal. So we can use them interchangeably. Then what we have to do is we have to remember our distributive property. So the next line we get 3x minus 8x plus 40 equals 12. Solving that for x, we get x equals 5.6. And then once we get an x value, we're not done yet. We have to go back and find our y value. So substitute the value of x into one of the original equations for y and solve for y. So we do that and we find that y equals -1.2. Okay, now a couple things here. It says substitute the value for x into one of the original equations and solve for y. Well, here are the original two equations. So they showed substituting 5.6 back in in the second equation. However, remember, this equation over here, that's equivalent. And when you do a substitution, the nice thing is that over here in step 3, you're solving for y. And over here you have an equation that's solved for y in terms of x. So just substitute that x value into this equation. I think that's a better option. Okay, so remember that our solution is an ordered pair, 5.6, -1.2. Our last lesson, we looked at solving these systems graphically. So if I were to graph these two lines, they would have an intersection point of 5.6, -1.2. But using the techniques that we learned in the last lesson, we would not be able to obtain those, or this solution, very easily without technology. So we have other methods that we can use to solve a system when the graphical method does not work. All right, here's an application of this. So our problem is an online music company offers 15 downloads for $19.75 and 40 downloads for $43.50. Each price includes the same one-time registration fee. What is the cost of each download and the registration fee? All right, so we're solving a system of equations is what we need to do here. We have two unknowns in this problem, and we have two situations, okay? So in a problem like this where you have two situations, you're working with them together simultaneously. What we have to do is we have to write a model for both situation, or an equation for both situation. Before we can come up with an equation, we need to define variables. So if we want to use x and y, we can. So our two variables, what is the cost of each download and the registration fee? So those are our variables. Okay, so let's let x equal the cost of a download, and let's let y equal the registration fee. So after we define our variables, we need to write two equations, and we have this first situation right here and our second situation right here. And this second sentence says each price includes the same one-time registration fee. So essentially what we're going to be doing is we're going to be writing two equations dealing with the price of this, these music downloads. All right, so what we've got to do is we got to take our cost per downloads plus our registration fee is going to equal the total cost, or the total price. So for the first situation, when we have 15 downloads, it says 15 downloads for $19.75. So we have 15 downloads times the cost of a download plus the registration fee, which we don't know, equals $19.75. The second equation, we know it's going to be 40x, okay? 40 downloads times the cost of a download plus that same registration fee equals $43.50. All right, so there's our system. So we're going to work with this system, these two equations together, all right? And so you can see here we have a y and we have a y, so this is a fairly decent substitution situation. So I'll just take my first equation and solve for y. So I get y equals negative 15x plus 19.75. And then I'm going to take this value, since it equals y, I'm going to take it and I'm going to substitute it in for y into the other equation, which gives me 40x plus the quantity, negative 15x plus 19.75. Okay? Always a good idea to, remember, anytime we substitute a value into an expression or an equation or a formula, it's always a good idea to put that quantity in parentheses in case we have some negative value in front or some coefficient that we have to distribute. In this case, that doesn't apply, but still a good habit to get into. Since this is just plus the quantity, we can go ahead and essentially drop the parentheses. And here's what we wind up with. So now if we solve this for x, 25x equals 23.75, divide both sides by 25, and we get x equals 0.95. So that x is the cost of a download. So one download costs 95 cents. So let's write that up here. Cost of a download, 95 cents. We're not done yet though. We're also asked to find the registration fee. So to find the registration fee, remember, we can go back to our original system if we'd like. But anytime we're doing substitution, it's always nice because we have the one equation is rewritten in terms of the variable that we're trying to find in terms of the variable that we just found. So let's go ahead and just evaluate this for 0.95. And that's going to equal 5.5. So the registration fee is $5.50. The cost of a download is 95 cents. Okay? So it would be appropriate for me to write a sentence that says the cost of a download is 95 cents and the registration fee is $5.50. Okay? Remember, anytime we're doing an application problem, we always want to write a sentence that answers the question that we're asked. Okay, let's talk about elimination, our other method here. Elimination is just like it sounds. What we're going to do is we're going to work with both of our equations here, and we're going to do something with those two equations so that one of the variables is eliminated, which allows us to solve a one variable equation leading to the solution of our system. Some other names for the elimination method are the addition method combination method and the multiplication method. The reason is because we use these components to solve the system when we are using the elimination method. We are going to add the two equations together so that one of the variables is eliminated. Another word for addition is combine, or so that's where we get the terminology of the combination method. And this could also be called the multiplication method, because if our system is not set up for the elimination to take place right away when we add the two equations together, it may be necessary to multiply one or both of the equations by some number so that when we do add them together, the elimination takes place. So here's an example that's worked out for us. What is the solution of the system of equations? And our two equations are 4x plus 2y equals 9, negative 4x plus 3y equals 16. Now, if you recall, if you've done the elimination method before, right away you would probably recognize here that in our system we have 4x and negative 4x. Okay? So over here, what we're going to do, this is already set up for elimination. We're going to write our two equations, and we're going to put our like terms vertically aligned from one another. So 4x plus 2y equals 9, and then right below that, negative 4x plus 3y equals 16. And what we're going to do is we're actually going to combine these together, or add them together. And when we add them together, these two, the 4x and the minus 4x, give us a 0. Okay, so that's why they're not written here. We have a 0. There's with the elimination. So 2y and 3y, those added together equals 5y. 9 plus 16 is 25. Divide by 5, we get a y value of 5. After we find y, we just need to go back and find x. So choose one of the original equations, and you can see that here. They chose 4x plus 2y equals 9. Substitute 5 in for y. Solve for x. X is negative 1/4. So the solution to the system is negative 1/4, 5. X value negative 1/4, y value 5. And recall what this means. Always think back to the graphical interpretation of this. If I were to graph these two lines, they would have an intersection point of negative 1/4, 5. Okay, so when we multiply each side of one or both equations in a system by the same non-zero number, the new system and the original system have the same solutions. The two systems are called equivalent systems, and we can use this method to make additive inverses. Okay, remember additive inverses, two numbers are additive inverses of one another if they combine to make a 0. Okay, so that's where this elimination happens. We need additive inverses in our equation on one of our variables for this elimination to take place. So if you look at our example here, we have 7x plus 5y equals 2. We have 8x minus 9y equals 17. As these two equations are, the elimination will not take place. If I add these together as they are, I'm going to get 15x minus 4y equals 19. Still have x, still have y. Algebraically, that does me no good. I can't solve this. All right, so what we have to do is we have to just be a little strategic about, maybe we multiply one of these equations by a number so that the elimination, we get an additive inverse here in this other equation. Or maybe we multiply the second equation by a number to produce an additive inverse in the first equation. But after we examine these two, there's nothing we can multiply 7 by to get an 8. And we want to use integers here. We don't want to use fractions and get too crazy with this. There's nothing we can multiply 7 by to get 8. There's nothing we can multiply 8 by to get 7. Same thing here with 5 and 9. If you can't do that, that's a big clue that we're actually going to multiply both of our equations by some value to produce these additive inverses. The big clue here, what's nice is we have an addition sign in the first equation and a subtraction sign in the second equation. So we already have the opposite signs set up here for the y's. So if we can create identical numbers here on y, when we go to combine these two equations together, we can eliminate y. So here's how I do this. If I can't make 9 from 5 and I can't make 5 from 9, what I'll do is I'll just multiply my first equation by 9, and I'll multiply my second equation by 5. Because when I do that, that gives me a positive 45 here and a negative 45 here. Those are additive inverses. Y will be eliminated when I go to combine these together. So what we're doing is we're creating an equivalent system. Okay? So I just have to multiply everything by 9 in the first equation, everything by 5 in the second equation. And when I do that, I get 63x plus 45y equals 18. The second equation becomes 40x minus 45y equals 85. Okay, now we have our additive inverse set up right here. So let's go ahead and combine these two equations. This kind of looks like an addition problem that we did back when we were, I don't know, second grade maybe, first grade. So anyway, let's go ahead and add our x terms together. So we get 103x, y is eliminated, and when we add our constants together we get 103. So 103x equals 103 is the equation that we have to solve. We divide both sides by 103, we find that x is 1. Okay? Take that x value and go back and plug it into one of our equations. If I plug 1 into my first equation, I get 7 times 1, which is 7, plus 5y equals 2. Subtract 7 from both sides, divide by 5, I get y is negative 1. So the solution to my system is 1, negative 1. Okay? So here I have another example for you. Go ahead and try this one. Pause the video and try it. And when you're ready, play it and I'll show you the solution. Okay. Anybody get a little confused here? If you chose to eliminate y, as we did in the previous example, then you would multiply the first equation by 3 and the second equation by 2, producing this equivalent system. If you chose to eliminate x, your system is probably going to look different. However, when you go to combine your two equations, x and y are eliminated, leaving 0 equals 65. So what does that mean? Well, that kind of leads into our next topic here in the lesson. Solving a system algebraically does not always provide a unique solution. Sometimes you get infinitely many solutions. Sometimes you get no solutions. So here are two examples. In example A, what are the solutions of the following systems? Explain. Well, if we use elimination here, the x's and the y's are eliminated, but when we go to combine negative 5 and 5, we get 0. We actually get a true statement here. If x and y are both eliminated, but we're left with a true statement, okay, a true equation, then what that does is that tells us that we have infinitely many solutions. We actually have identical or equivalent equations, right? They don't look equivalent, but they are, okay? Example B here, x and y are eliminated. We add 6 and 10, we get 16, so we have a statement that 0 equals 16, we know that that's false. So this tells us that our system has no solutions, okay? So, and again, if you remember what this means graphically, in A, same line. We call that coincide. The lines coincide. Here, what does this mean? Parallel lines. Okay, that's what we get when we have no solution, right? So that last example that I had you guys try, that was an example of a system that has no solutions. The lines are parallel, okay? If I flip back here for just a second, you know, if I were to take these two equations and rewrite them in slope-intercept form, those two equations would both have the same slope. They're going to have different y-intercepts though. So that tells us that those two lines are going to be parallel. All right, I hope you guys have a great day.